February 1945, 30,000 feet above Japan. The air is thin enough to burn the lungs if the cabin seal fails. Frost creeps along metal frames. Engines drone with a steady violence that never quite fades into the background. Inside the pressurized fuselage of a Boeing B-29 Superfortress, warning lights flicker not all at once, but enough to be noticed. A gauge drifts off its mark, then another. Somewhere aft, a vibration changes pitch. Outside, dark shapes climb toward the formation. Japanese interceptors rise fast, trading altitude for position. The B-29 is supposed to be untouchable up here too high, too fast, too heavily armed. But that promise depends on systems working exactly as designed, and one of them is not. A remote gun system hesitates. A turret stops responding the way it should. The bomber begins to lag just slightly, just enough. There is no checklist for what happens next. One crewman leaves his station, grabs a toolman for maintenance, not combat, and makes a decision measured in seconds. No order is given. No discussion follows. Metal scrapes. A connection changes. Moments later, 7 attackers will not return, and the bomber will. To understand how something so small could matter so much, it is necessary to step back into the machine itself and the war that forced men to trust it. With their lives, the Boeing B-29 Superfortress was not simply another bomber. It was a leap technological, strategic, and operational pushed into service before anyone fully understood its limits. Designed to fly higher, farther, and faster than any bomber before it, the B-29 introduced features that belonged as much to the future as to World War II. Pressurized crew compartments allowed sustained operations above 30,000 feet. Remote-controlled gun turrets, aimed by analog fire control computers, reduced drag and improved defensive coverage. Powerful engines promised unprecedented performance. On paper, it was unstoppable. In reality, it was fragile. The B-29 entered combat in 1944. With systems so complex that no previous bomber crew had encountered anything like them. Pressurization meant that a single failure, a cracked seal, a jammed door, a damaged bulkhead could instantly turn the aircraft lethal to its own crew. Remote turrets relied on miles of wiring, motors, and relays that behaved differently in extreme cold and thin air, and the engines, operating at the edge of their thermal limits, were prone to fires that spread faster than crews could react. Early operations revealed the cost. During the initial deployments from China and later the Marianas, B-29 losses often occurred without enemy contact. Aircraft burned on takeoff. Systems failed at altitude. Crews were forced to bail out over ocean or hostile territory because a single subsystem malfunction cascaded beyond control. These were not training accidents. They were combat realities. Yet the mission demanded persistence. The B-29 was the only aircraft capable of striking the Japanese home islands with meaningful payloads. There was no alternative. Crews learned to fly machines that behaved differently every mission. Procedures were written, revised, and quietly ignored when experience contradicted theory. Inside the aircraft, specialization was absolute. Each crewman operated a narrow slice of the bomber's systems. Gunners trusted the fire control computers. Engineers monitored engines constantly. Navigators and radar operators worked in sealed compartments separated by pressure tunnels. In combat, coordination depended entirely on systems functioning as designed. When they did not, improvisation became survival. This environment created a paradox. The B-29 was designed to reduce human exposure mote guns, automation, pressurization. But when automation failed, only human judgment could compensate. And that judgment had to be exercised instantly, often by men trained to follow procedures, not invent them. As the bombing campaign intensified in late 1944 and early 1945, Japanese defenses adapted. Interceptors climbed higher. Attacks became more aggressive. B-29 formations encountered increasing pressure precisely when the aircraft systems were most stressed by cold, altitude, and fatigue. In this context, Single malfunction was never isolated. It threatened the entire aircraft, and when a B-29 lagged behind formation even slightly, it became a magnet for interceptors trained to exploit weakness. What followed was often swift and fatal. The scene unfolding over Japan in February 1945 was not unusual in its danger. What made it different was what happened next when a complex system failed in combat, and one crewman chose not to wait for orders. To understand why that choice mattered, it is necessary to examine the other side of the encounter, the men climbing toward the bomber, the doctrine that guided them. By the time B-29 formations began appearing regularly over the Japanese home islands, Japan's air defense doctrine had narrowed to a single, urgent purpose: stop the bomber before it could release its load. High altitude changed everything. The Imperial Japanese Army Air Service and Naval Air Units were forced to adapt aircraft never designed for sustained operations. Above 30,000 feet, engines lost power, controls stiffened. Pilots climbed at the edge of their machines' capabilities, knowing they would have only minutes, sometimes seconds, to attack before fuel, oxygen, or altitude ran out. Interceptors like the Nakajima Ki-44 Shoki and the Kawasaki Ki-61 Hine were fast climbers by Japanese standards, but they paid for that performance in stability and endurance. Pilots trained to make short, violent passes rather than prolonged engagements. Ammunition was limited. Visibility was poor. Recovery windows were unforgiving. This produced a specific attack pattern. Japanese pilots targeted stragglers, a B-29 that drifted out of formation because of engine trouble. System lag or minor damage was immediately marked. Formation fire could be evaded. Isolated bombers could be swarmed. Attacks came from head-on, from below, and increasingly from the rear quarter, where approach angles reduced exposure time to defensive guns. These attacks relied on precision and timing. The B-29's remote-controlled gun system, when fully functional, was formidable. Overlapping fields of fire, centralized fire control computers, and heavy-caliber weapons created defensive zones that Japanese pilots learned to respect. But that respect vanished the moment a turret failed or lagged. A non-responsive gun was not just a gap, it was an invitation. Japanese pilots were trained to recognize subtle cues, changes in tracer patterns, delayed responses, blind arcs. A few seconds of hesitation from a turret could reveal an entire defensive weakness. Once identified, the attack intensified. Multiple fighters would converge, forcing the bomber's remaining gunners to divide attention and overheat systems already under strain. This doctrine assumed one thing above all else: predictability. B-29 defenses were complex, but they were supposed to behave consistently. When a turret stopped tracking, it stayed stopped. When a system failed, it failed safely or not at all. Japanese pilots counted on that reliability to calculate risk. What they did not account for was human interference. The B-29's designers never intended for crewmen to bypass or modify defensive systems in flight. Maintenance tools existed, but only for ground crews. In combat, the expectation was that systems either worked or did not, and that crews adapted tactically, not mechanically. Yet the pressures of high-altitude interception created moments where the boundary between operator and maintainer collapsed. Above Japan in early 1945, interceptors climbing toward a faltering bomber believed they were facing a known machine with known limits. They expected gaps to remain gaps. They expected responses too slow as systems overheated and crews became overwhelmed. They did not expect a defensive system to behave differently mid-attack, and it was precisely in that expectation shared by pilots, engineers, and doctrine. The smallest deviation could have outsized consequences, because when a system designed for automation was suddenly altered by human hands, the entire logic of the interception began to unravel. What followed was not a planned tactic, nor a designed feature. It was an improvised response, executed in seconds, inside a freezing aircraft under attack, where a single tool, used in a way no manual described, would change how the engagement unfolded. A B-29 crew functioned as a distributed organism, separated by pressure bulkheads and narrow crawl tunnels. Each man depended on instruments, voices over intercom, and the assumption that systems would respond as expected. In combat, those assumptions were tested relentlessly. Cold, stiffened metal. Altitude, dulled sensation. Noise masked, subtle changes. Until they became problems. When a system faltered, the first response was procedural. Call it out, recheck the indicator, cycle the control. But procedures assumed time. Interceptors climbing toward the aircraft removed that luxury. Asterisk. The crewman who noticed the hesitation in the remote gun system was not acting in isolation. He heard the pilot's voice tighten. He heard gunners reporting contacts converging. He felt the bomber sag as power fluctuated. He understood instinctively that the margin was collapsing. What followed was not heroics, but judgment. Leaving one station in a pressurized aircraft at altitude was itself a risk. Moving through the fuselage under G-load and vibration demanded care. Yet the choice was immediate. Accept a known failure or attempt a correction no checklist authorized. The decision was made without ceremony because hesitation would invite swarm tactics the crew had seen before. In that moment, coordination became implicit rather than spoken. Others continued to fight their stations, buying seconds. The aircraft held together long enough for a human intervention to occur. The B-29's remote-controlled gun system was a marvel of its time and a liability under stress. Gunners did not sit behind their weapons. They aimed through sighting stations linked to turrets by motors, servos, and analog computers. Signals traveled through wiring looms exposed to vibration and extreme cold. When everything aligned, multiple turrets could be slaved to a single sight, concentrating fire with remarkable accuracy. When something slipped, the effect was immediate. A momentary loss of synchronization could cause a turret to lag, overshoot, or stop responding altogether. At altitude, lubricants thickened. Electrical contacts behaved differently. Small mechanical tolerances widened just enough to matter. A non-responsive turret did more than reduce firepower. It altered geometry. Japanese interceptors probed constantly. For blind arcs, hesitation in response told them where to commit. If a rear upper turret lagged, attack shifted to that quarter. If a side turret failed to track smoothly, head-on passes became more aggressive, forcing the bomber to absorb punishment until formation support could intervene. The tool hack that followed did not create new capability. It restored predictability, using a maintenance tool standard issue for in-flight adjustments where permitted the crewman altered a mechanical interface in the control linkage. The action bypassed a sticking component, trading finesse for immediacy. The turret's motion became less refined, but more responsive. Tracking improved. Dead time vanished. The system was no longer operating as designed. It was operating as needed. Japanese interceptor tactics relied on rapid assessment. Pilots climbed hard, expending precious fuel and oxygen to reach the bomber stream. Once contact was made, they evaluated risk quickly. If defensive fire was dense and coordinated, they disengaged and sought another target. They sensed hesitation. They committed. The lagging turret had done exactly what doctrine predicted. It advertised vulnerability. As interceptors closed, they expected the pattern to hold. Instead, tracer arcs shifted abruptly. Fire came earlier and from angles that should have remained cold. The bomber's defensive envelope changed mid-attack. This mattered tactically. Japanese pilots committed to attack runs based on timing. When that timing was disrupted, escape windows closed. A fighter entering a head-on pass counted on a brief exposure. When fire arrived sooner, closure rates worked against the attacker. In a stern chase, a turret that regained responsiveness compressed distance fatally dut. Over the course of the engagement, multiple fighters attacked in sequence rather than simultaneously, standard practice to exploit openings without colliding. As each attack met unexpectedly dense fire, the pattern compounded. Damaged aircraft shed altitude. Others broke away too late. The bomber's guns did not become deadlier. The interceptor's margins became thinner. Claims recorded afterward credited to the bomber's gunners during that single engagement listed 7 enemy aircraft destroyed. In the fog of high-altitude combat, exact confirmations were always difficult. What mattered operationally was that the attacks ceased. The bomber rejoined formation. The improvised correction had not turned the B-29 into something new. It had restored the machine to a state Japanese pilots believed no longer existed. Predictability returned on American terms. These three angles: human judgment, a tactical restoration, and tactical disruption, explain how seconds and millimeters mattered at altitude. They also reveal a deeper truth. In complex systems, failure does not always announce itself catastrophically. Sometimes it whispers, inviting exploitation. The next angles will show how that invitation was misunderstood by the enemy, how improvisation spread quietly among crews, and how a single deviation in a machine-centric war exposed the limits of doctrine on both sides. Improvisation in the air was, to me, never encouraged. It was tolerated only because the alternative was often fatal. The B-29 systems were designed to remove variability. Automation reduced human error. Standard procedures promised consistency across crews and missions. Yet the reality of high-altitude combat exposed a contradiction. The more complex the system, the more brittle it became when stressed beyond design margins. The crewman's action did not create a new tactic. It restored continuity by using a simple maintenance tool to bypass a sticking interface. He accepted a trade the designers never intended: precision for immediacy. The turret no longer tracked with textbook smoothness. It responded without delay. In a fight measured in fractions of a second, that difference mattered more than elegance. No manual authorized this. No checklist described it. But the aircraft did not protest. The system stabilized. Fire returned where it was expected. The bombers stopped advertising weakness. This kind of improvisation rarely entered official doctrine because it was context-dependent and risky. What worked once might fail elsewhere. Yet crews remembered such moments. They shared them quietly, not as instructions, but as possibilities, options to consider when everything else ran out. Japanese interceptor pilots were trained to read bombers like terrain. Tracer density, timing, and arc revealed where to attack. A momentary gap meant commitment. Doctrine assumed that once a system faltered, it would continue to falter. That assumption guided risk calculations during the climb and the attack run. In this engagement, that assumption failed. As interceptors pressed in, they encountered a defensive pattern that changed without warning. Fire arrived earlier. Once safe, were suddenly hot. The bombers' behavior violated expectations built from dozens of previous encounters. This misreading had consequences. Japanese pilots committed based on a snapshot what the bomber looked like seconds earlier. At high closure rates, there was no time to reevaluate. When the defensive envelope reasserted itself, attackers were already inside it. Damage followed quickly. Recovery options narrowed. From the Japanese perspective, the machine had lied. The B-29 they thought they understood was no longer consistent. That inconsistency was deadly, not because it increased firepower, but because it invalidated timing. In air combat, timing is survival. Complex systems fail in chains. A slight electrical lag becomes a mechanical hesitation. That hesitation becomes a tactical gap. The gap attracts attention. Attention concentrates force. Force amplifies stress. Stress accelerates failure. The tool hack interrupted that cascade by restoring responsiveness at a single node. The crewman altered the system's behavior as a whole. Other turrets no longer had to compensate. Gunners regained confidence in what they were seeing. The pilot could maintain formation instead of maneuvering defensively. The aircraft's profile to the enemy stabilized. This is how complex machines survive combat, not by avoiding failure, but by recovering from it quickly enough to deny exploitation. The engagement's outcome credited as 7 interceptors destroyed must be understood in this context. High-altitude claims were conservative estimates at best. What is verifiable is that multiple attacks were broken off and the bomber rejoined its formation intact. The defensive system's recovery ended the window of vulnerability Japanese doctrine depended upon. After landing, the aircraft showed evidence of stress and damage consistent with a concentrated interception. The crew debriefed. The incident was noted without fanfare. No recommendation followed to replicate the action. Officially, nothing had changed. Unofficially, something had. Crews learned that the B-29's automation could be negotiated with carefully, intelligently when conditions demanded it. They learned that a machine designed to remove human intervention still relied on human judgment at the edge. These lessons rarely appeared in manuals. They traveled through conversations, through reputation, through the quiet confidence of crews who had survived moments others did not. As the bombing campaign continued, the skies over Japan grew more dangerous and more predictable at the same time. Interceptors became more desperate. Bombers became more experienced. The balance tilted not because of one tool or one action, but because complex systems on both sides were reaching their limits. All of these pressures converged in a single window of time over Japan, where seconds decided whether a bomber would fall away or hold its place in the stream. The next section follows that convergence when the failure escalated. The choice was made, and the engagement resolved with consequences that rippled far beyond one aircraft. The escalation began quietly, the way most catastrophes do in the air at cruising altitude. The bowing B-29 Superfortress settled into the long approach toward its target. Engines were balanced. Bomb bay doors were still sealed. Formation spacing held steady. To the crew, the aircraft felt almost normal and illusion that rarely lasted. Then the interceptors arrived. Radar warnings turned into visual contacts. Dark specks rose through the haze below, climbing with determination born of desperation. The pilot adjusted slightly to maintain position, careful not to drift. Formation was protection. Separation was death. The first attack came head-on. Tracer fire stitched the air ahead of the bomber. The gunners responded immediately, but one turret lagged a gange just enough to be noticed. The hesitation was subtle, but it widened the bomber's profile. The second pass came faster. A third followed close behind, tighter, more confident. Inside the aircraft, the sense of compression grew. The flight engineer called out engine temperatures edging upward. Gunners reported contacts stacking on the same quarter. The pilot felt the bomber's mass resist small corrections, as if the aircraft itself sensed the danger and braced against it. This was the moment Japanese interceptor doctrine waited for. Multiple fighters committed simultaneously, counting on the defensive gap to hold long enough to overwhelm the remaining turrets. At high closure speeds, there would be no second chance. Either the bomber's fire disrupted the attack immediately, or the attackers would reach firing range. The crewman, who had already intervened, once understood the stakes instantly. The earlier adjustment had restored responsiveness, but the stress of sustained firing and vibration was pushing the system again. The lag threatened to return. There was no time to analyze, no time to consult. He acted again, this time more decisively. The tool came out. A panel was forced open further. The linkage was locked in place by feel, not measurement. The action sacrificed refinement entirely. What mattered now was whether the turret would move when commanded. It did. The change was immediate and unmistakable. Tracer streams shifted sooner. Coverage overlapped where it had not seconds earlier. The attacking fighters flew into fire that arrived ahead of expectation. Collapsing their timing, one interceptor peeled away, trailing smoke. Another failed to pull out cleanly and vanished downward. The formation of attackers broke into fragments, each pilot now reacting alone instead of as part of a pattern. This was the turning point. The bomber did not maneuver aggressively. It did not chase. It held position and let the restored system do what it had been designed to do: deny approach. Within moments, the intensity of the attack faded. Remaining fighters disengaged, unable to exploit a vulnerability that no longer existed. The B-29 absorbed the last of the tracer fire and steadied. Inside the aircraft, no one spoke. There was nothing to say. The crisis had passed, not because the bomber became invulnerable, but because a narrow window had been closed in time. The formation closed ranks. The bomber slipped back into the stream, indistinguishable once again from its neighbors. The mission was not over. Bombs still had to be dropped. The return flight still loomed. But something irreversible had already occurred. A failure that should have doomed the aircraft had been arrested mid-fall, and as the formation pressed on toward its target, the crew understood without articulating it that survival had hinged on a choice no doctrine had anticipated. The consequences of that choice would only become clear later, when the engagement was tallied and the reality of what had just happened began to settle in. The fight did not end with silence. It ended with separation as the remaining interceptors broke away. The bowing B-29 Superfortress continued straight and level, its course unchanged. This was not restraint, it was discipline. Any abrupt maneuver risked reopening the very vulnerabilities that had just been sealed below. Fragments of the engagement fell away into cloud and distance. The gunners stayed locked on their sights, scanning for renewed climbs. The pilot held formation speed precisely. The flight engineer kept engine temperatures within a narrowing band. The bomber did not accelerate or descend. It presented no new problem for the enemy to solve. That choice mattered. Japanese interceptor. Doctrine depended on repetition, multiple short attacks to exhaust defenses and force mistakes. But repetition required predictability. When the bomber's defensive pattern stabilized, the cost of re-engagement rose sharply. Fuel and oxygen margins were already thin. Damaged aircraft could not rejoin. Pilots who had lost timing could not reset it. One by one, the attackers disengaged. Later, during the return leg, the crew would piece together what had happened from fragmented reports. Gunners had tracked separate targets. The fire control system, now operating without hesitation, had allowed overlapping fields of fire to converge repeatedly. Several interceptors were seen breaking apart under concentrated fire. Others vanished. After failing to recover from steep pullouts at altitude, claims were recorded conservatively. As procedure required, 7 enemy aircraft were credited as destroyed in that engagement. Whether all 7 were confirmed by wreckage or only by consistent observation mattered less than the operational result. The attacks had ceased. The bomber had remained in formation. The mission continued. That continuation was the true measure of success. The bombs were released on schedule. The formation turned for home. The long flight back carried its own risks: fuel consumption, engine strain, navigation through weather, but the bomber was no longer singled out. The enemy had lost its opening inside the aircraft. The improvised fix held. The turret's movement remained coarse but immediate. Gunners adjusted. Fire discipline compensated for the lack of finesse. The system did not revert. It endured long enough to remove the bomber from danger. When the aircraft finally landed, ground crews discovered the signs of stress everywhere: scored panels, heat damage near an engine nacelle, wiring chafed by vibration. The improvised adjustment was noted, then quietly reversed during maintenance. The aircraft returned to standard configuration. Officially, the incident became a line in a debrief. Unofficially, it became something else. Crewmen across units understood the lesson without being told. The B-29's strength lay not only in its systems, but in the space it allowed for human judgment when those systems faltered. The aircraft had survived because a failure had been arrested before doctrine could exploit it. From the Japanese perspective, engagement closed as abruptly as it had opened. A bomber that should have been vulnerable had suddenly become opaque again. Timing failed. Risk spiked. The opportunity passed. This is how air battles often end, not with annihilation, but with denial. The denial of a second pass. The denial of a pattern. The denial of certainty. And as the bomber stream faded toward the horizon, the consequences of that denial began to ripple outward into debrief rooms, maintenance hangars, and quiet conversations where crews tried to articulate what had saved them. Those consequences would shape how the B-29 was flown for the remainder of the war, not through new checklists or official amendments, but through an understanding shared by men who had seen how thin the margin could be. The consequences began on the runway, when the bowing B-29 Superfortress rolled to a stop and engines wound down. Ground crews moved in with practiced speed. They expected damage. They always did. But as panels were opened and systems inspected, it became clear how close the aircraft had come to being lost. Heat scoring near an engine. Nacelle suggested sustained stress at combat power. Wiring bundles feeding the remote gun system showed signs of vibration and cold-induced stiffening. The turret linkage that had been improvised in flight bore marks no checklist could explain. Asterisk, nothing catastrophic had failed. That was the point in the debrief room. The crew spoke carefully. Air crews were trained to report facts, not interpretations. A system had lagged. An adjustment had been made. Defensive fire had been effective. Enemy attacks had ceased. 7 interceptors were credited, subject to confirmation. The aircraft had completed its mission. There was no recommendation attached. The absence was deliberate. B-29 operations were governed by tight procedural control. Any unofficial modification carried risk if misunderstood or misapplied. Commanders were wary of encouraging in-flight mechanical improvisation, knowing that one misjudgment could depressurize a compartment or cascade into worse failure. Yet the lesson did not disappear. It traveled laterally. Other crews heard about the incident not through bulletins, but through conversation maintenance sheds, briefing lines, quiet moments before takeoff. The story was not framed as a technique to copy, but as a reminder. Systems could be negotiated when time ran out. Asterisk, this understanding altered behavior subtly. Gunners paid closer attention to lag, not just failure. Engineers listened for changes in vibration patterns that hinted at impending problems. Crewmen grew more willing to leave stations briefly when a narrow fix might prevent a larger collapse. No one spoke of hacks. They spoke of judgment for Japanese air defenders. The immediate consequence was simpler. The bomber had survived. Interceptor units recorded the engagement as another failed attempt against a formation that refused to break. Losses were noted. Pilots reported unexpected defensive density during what should have been a vulnerable window. The reports were filed alongside many others, describing bombers that seemed inconsistently dangerous. Asterisk, no doctrinal change followed. Japan's air defense system was already strained beyond its ability to adapt. Fuel shortages, limited training. Aircraft were lost faster than they could be replaced. The notion that a bomber crew might alter a system mid-combat did not fit existing models of enemy behavior, and so it was not pursued. This mismatch mattered. On one side, air crews absorbed a lesson about human agency within machines. On the other, interceptors continued to plan attacks around assumptions of predictable failure. Each subsequent engagement widened that gap. The B-29 program itself absorbed the incident only indirectly. Engineers continued refining reliability. Maintenance procedures improved incrementally. But no manual captured the moment when a crewman closed a fatal window with a tool meant for another purpose. Those moments rarely survive in official records, yet they shape outcomes. As the bombing campaign intensified in the spring of 1945, more B-29s flew more often under greater pressure. Systems failed. Crews adapted. Most adaptations remained invisible, folded into the broader pattern of survivability that defined the aircraft's late-war record. The incident over Japan did not change the war on its own, but it illustrated something essential about how the war was being fought now at the edge of technology, where success depended not just on design or doctrine, but on the ability of individuals to act decisively inside machines that were never meant to improvise. That realization would deepen as the campaign continued, shaping how crews thought about survival long after that single mission ended. As weeks passed, the incident dissolved into the rhythm of operations. Missions launched, bombs fell, aircraft returned or did not. The war's scale absorbed individual moments the way altitude absorbs sound. Yet within that vast machinery, the lesson persisted, quiet and precise. The bowing B-29 Superfortress continued to fly at the edge of possibility. Its systems improved incrementally, but never became simple. Pressurization still failed. Turrets still lagged. Engines still flirted with their limits. And crews still faced moments where procedure ended before danger did. What changed was not doctrine, but awareness. Crewmen understood that the aircraft's automation was not absolute. It was conditional. It worked brilliantly until it did not. When that boundary appeared, survival depended on recognizing it early enough to act, not boldly, not creatively. Precisely. Maintenance officers noticed a pattern they did not formally name. Aircraft that survived intense interceptions often showed signs of in-flight adjustment panels disturbed, linkages stressed, settings altered and then restored on the ground. No one encouraged this. No one punished it either. The priority was return for Japanese defenders. The pattern was harder to read. Interceptor pilots continued to report bombers whose defensive fire shifted unexpectedly. Attacks that should have succeeded failed without obvious explanation. The gap between expectation and outcome widened, but the resources required to investigate it were no longer available. Japan's air defense system was unraveling. Fuel shortages grounded aircraft. Training time collapsed. Veteran pilots were gone. New pilots flew missions with only basic preparation, facing bombers that behaved unpredictably under fire. The assumption that a damaged or lagging system would remain exploitable became increasingly unreliable. This mattered even as the nature of the bombing campaign changed. Low altitude. Incendiary raids placed different stresses on B-29s, but the lesson endured. Systems failed differently. Crew judgment remained decisive. The aircraft's late-war survival rates reflected not perfection, but adaptation, human and mechanical interwoven. In post-war analyses, the B-29's effectiveness was measured in tonnage, accuracy, and reach. Its vulnerability was cataloged in engine failures and early losses. Rarely mentioned were the moments between when crews prevented catastrophe without instruction or recognition. Those moments resisted documentation. They did not fit forms. They did not scale. They could not be taught universally. And yet, they occurred often enough to matter. The B-29 did not survive the war solely because it was advanced. It survived because men inside it refused to accept failure as final. The incident that credited 7 interceptors destroyed stands as an extreme example, but not an isolated one. It illustrates how outcomes sometimes hinge not on designed capability, but on the speed with which a system can be returned to predictability. Predictability denied opportunity. Opportunity denied attack. Attack denied loss. As the war neared its end, the bomber stream grew ever more confident, not because danger had vanished, but because crews had learned how to navigate complexity under pressure. The B-29 became less mysterious, not more reliable, understood in its weaknesses as well as its strengths, and that understanding set the stage for a broader reflection on how modern war was being fought inside machines where survival depended on the space between automation and human choice. Modern war is often described as a contest of machines, bigger, faster, more complex. Yet the story of the B-29 reveals a quieter truth beneath the noise of engines and the glare of explosions. Complex machines do not eliminate human judgment. They compress it. The Boeing B-29 Superfortress was built to reduce reliance on the human body, pressurized cabins, remote guns, automation layered upon automation. But when those systems faltered at the edge of their design envelope, survival returned to something older and simpler: recognition, decision, action. The crewman who reached for a tool did not invent a new weapon. He did not outthink an enemy, doctrine, or defy engineering. He closed a gap quickly enough that doctrine could not exploit it. That was all, and it was enough. 7 interceptors destroyed is a striking number, but it is not the heart of the story. The heart lies in the fact that the bomber returned, that the mission continued. That failure did not propagate because someone intervened before it could dot. Wars are often decided not by grand innovations, but by thousands of small moments where systems almost fail, do not. Those moments rarely appear in official histories. Because they resist replication, they depend on context, experience, and restraint as much as courage. In the skies over Japan, the B-29 represented the future of warfare: complex, automated, unforgiving. But inside that future, means still mattered in ways no blueprint could anticipate. The lesson endures. As technology advances, the margin for error narrows. Automation grows powerful, land brittle. When failure arrives, it rarely asks permission. Survival belongs to those who recognize the moment when procedure ends and judgment begins. That is how a bomber lived. That is how 7 attackers fell. And that is how, in a war defined by machines, one unplanned human action quietly altered the outcome of a single mission without changing a single line in a manual.